Okay, so if we're looking at how LeChatelier's principle applies to systems at equilibrium, the reaction is always going to shift to relieve the stress that's applied. So it's going to shift either to the right-hand side, RHS, or to the left-hand side in order to relieve whatever stress has been applied. So in this first example on page 13, the reaction of nitrogen plus 3 hydrogen to form 2 NH3, that reaction is exothermic. The delta H is given as negative 92 kilojoules per mole, which means that heat can be considered to be a product. And so when it's an exothermic reaction, go ahead and write the word heat in as a product. If it's an endothermic reaction, you would consider heat to be a reactant. Remember, for exothermic, heat is given off to the surroundings from the system, and so heat moves out of that reaction and into the surroundings. And so we treat it like a product, and that's going to help us figure out which way the reaction shifts when we change the temperature. So let's walk through these shifts and talk about them. If we increase the pressure or decrease the size of the container, remember that's the stress that's going to shift to the fewer moles of gas. On the reactant side, we have 1 nitrogen to 3 hydrogen, so a total of 4 moles of gas on the left. And on the product side, we have 2 moles of gas. So increasing the pressure or decreasing the volume is going to cause a shift to the right-hand side. It's going to make more product in order to relieve that stress. The way you can think about that is that Q would be small, and so the reaction is going to have to move forward or to the right to make Q equal to K. To bring that system back into equilibrium, we're going to have to shift to the right. All right, so increasing the temperature says it shifts to the left. Why is that true? So if we increase the temperature, what we're doing is effectively adding a product. We're adding something to the right-hand side. And so when we add a product, we have to shift to the reactant side to balance that stress. And so it's the exact same effect that we would see if we added NH3. If we increased the concentration of NH3, we would also shift to the left to reduce that stress to reach equilibrium. Increasing the concentration of nitrogen and hydrogen, those are our 2 reactants. If I increase either one or both of those, the reaction will shift to the right in order to relieve that stress. So Q would have to be decreased. Q would be lower than K, and so to get it back equal to K, shift to the right. Increasing the concentration of ammonia, that's a product, so that's adding a product, that will shift us to the left. On the second example, number 2, hydrogen gas plus iodine gas produces 2HI, and this one is an endothermic reaction, and so we consider heat to be a reactant. I wrote that in for you there. And so what's going to be the effect of increasing the pressure on this reaction? No effect. Why? Can you justify that? So I've got 1 mole of hydrogen plus 1 mole of iodine on the left, and then 2 moles of hydrogen iodide on the right. So 2 moles of gas to 2 moles of gas. There's no change in moles of gas on both sides of the reaction. And so neither side would be favored. It would have no effect. All right, if I increase the temperature for an endothermic reaction like this one, heat is considered to be a reactant, and so increasing the temperature will cause that reaction to shift to the right to form more HI. If you increase the concentration of hydrogen and iodine, it says and, it could be or, either one, we're going to get the same effect, and that's going to be a shift to the right. Increasing the concentration of our HI is going to, HI's product, so that's going to cause a shift to the left. A nice note at the bottom of that, a catalyst. What does a catalyst do? How is that going to cause it to shift? Well, what a catalyst does, you'll remember, is it lowers the height of the activation energy between your reactants and products. And so we can reach equilibrium faster, but the equilibrium position would stay the same. And so it affects the kinetics, but it does not affect the equilibrium position. So it affects the forward and reverse reactions equally, and so we would just reach equilibrium a little bit faster or a lot faster, depending on the reaction. So looking through the rest of these notes on this topic, let's highlight a few things here. Increasing the temperature causes a larger increase in the rate of reaction with larger activation energies. Increasing the temperature will always shift an equilibrium in the endothermic direction. What is the endothermic direction? Well, the endothermic direction, if it's an endothermic reaction, then your products are higher in energy than your reactants, and that results in a positive delta H, and this is our typical energy diagram for an endothermic reaction. We think of this as an exothermic diagram, but this could also be an endothermic in reverse. If you look at this backwards, if we're moving from the products to the reactants, then that process, if it's exothermic in the forward direction, it will be endothermic in the reverse direction. And increasing the temperature will shift it in the endothermic direction. So if you remember that, that may help you out as well. All right. KSP is a new idea. I told you we'd see several Ks. KSP is the equilibrium of solubility, and so we call this the solubility product constant. And it looks a little bit, it's the same, it's the ratio of the products to the reactants. Why is my video doing that? The ratio of the products to the reactants, but the reactant is always going to be a slightly soluble ionic compound that's only partially soluble. I don't know if my video is going to go out completely. I'm not sure what's going on here. But remember, we omit pure solids from our K expression. So K for the dissolution of a sparingly soluble salt is just the two ions that are formed from that reaction. So K, just like Kc, Kp, KSP would be concentration of products to the P over reactants to the R, but you will never have anything on the bottom because this reactant is just, it's always going to be the pure solid. And so we just end up omitting that. Read through this, and you guys see if you can work through task 7.4 on your own, and we'll go through that in a video tomorrow. Bye.